Bismillah, Alhamdulillah, wassalatu wassalamu ala Rasulillah. This is section 11.6. We have two tests in this section, the ratio test and the root test. And we will start by the ratio test. Uh, the ratio test says we take absolute value of an plus 1 over an. When we have a series like this, an is the nth term, and you find an plus 1, the nth plus 1 term, and you find this term by replacing n by n plus 1 in the series. So for example, here in this series, an is negative 1 to the power n times n to the power 3 over 3 to the power n, while an plus 1 would be replacing n by n plus 1. So it's negative 1 to the power n plus 1. And then n plus 1 to the power 3. And then 3 to the power n plus 1. And now the ratio test asks you to find the absolute value of an plus 1 over n. So the absolute value of an plus 1 over an would be the absolute value of negative 1 to the power n plus 1 times n plus 1 to the power 3 over 3 to the power n plus 1 divided by an. And an is negative 1 to the power n times n to the power 3 times 3 to the power n. And now the division changes to multiplication. So I have negative 1 to the power n plus 1, n plus 1 to the power 3 over 3 to the power n plus 1 times. And from now on, I will not write the division. I will always write it multiplication by the reciprocal of an. So this is the reciprocal of an, n to the power 3, not 3 to the power n. And now, if there is any cancellation, you cancel. Now, 3 to the power n, and this is 3 to the power n plus 1. 3 to the power n plus 1, I can write it 3 to the power n times 3 to the power 1. Because when you multiply, you add the powers. So I can cancel these two. Also here, I have negative 1 to the power n plus 1 and negative 1 to the power n. So this is negative 1 to the power n times negative 1. And I can cancel this with this. So I will have n negative 1 and n plus 1 to the power 3 over I have 3 times n cube. So this is the first step in using the ratio test. I find the absolute value of an plus 1 over an. And then I find the limit of this absolute value. Of course, the absolute value would be still the negative 1. Absolute value of negative 1 is positive 1. N plus 1 is positive because n starts from 1 to infinity. And 3 is positive and n cube is positive. So this is the absolute value of an plus 1 over n. Let us now find the limits of this quantity when n goes to infinity. And this is what the test says. Find the limit when n approaches infinity of this absolute value. How to find the limit of the limit when n approaches infinity, we take the uh, term with the highest power from the numerator. When I expand this, I'll get n cube and other terms, but n cube would be the term with the highest power. And I have 3 n cube. N cube cancels with n cube, and I'll get 1 over 3. So that's the limit. So now, what does the ratio test says? Now L, now L is this 1 over 3. So this 1 over 3 is the capital L the test says, the test is talking about. The test says if L is less than 1, then this series is absolutely convergent, therefore convergent. So 1 over 3 is actually greater than 1. So I just say that this is less than 1. Then I say by ratio test, summation AN is absolutely convergent, where this is AN, okay, summation AN. So this is very simple, the ratio test. If L is greater than 1, the series is divergent. If L is equal to 1, the ratio test is inconclusive. So the test fails. And you have to find you have to use other tests if the ratio, if L is 1, if the limit is 1. Another example. So let us start by finding absolute value of AN plus 1 over AN. And this would be N plus 1 to the power N plus 1 over N plus 1 factorial. This is AN plus 1 multiplied by the reciprocal of AN, which is N factorial over N to the power N. Of course, everything is positive inside, so I can just get rid of the absolute value. And now uh, N plus 1 factorial can be written as N plus 1 times N factorial. And I can cancel N factorial with N factorial. So I will have uh, N also, I have N plus 1 to the power N plus 1. And here N plus 1 to the power 1. So when I subtract the powers, I'll have N plus 1 to the power N. Okay, plus 1 minus 1. Over, I have here N to the power N. So this is the absolute value. Now I need to find the limit when n approaches infinity of this quantity. Okay, I can write it n over n1 plus 1 over n. I can write it like this. Well, it is known that this limit is e. We have seen this in calculus 1. Let me prove it again here using the L'Hopital's rule, but you can, after that, you can just use it as a rule. If I replace n by infinity, I will have 1 plus 1 over infinity 0. I'll have 1 to the power infinity. So using L'Hopital's rule for the function 1 plus 1 over x to the power x, I have 1 over infinity, 1 to the power infinity, sorry. So I let y equals 1 plus 1 over x to the power x. That's how we deal with this indeterminate form. And then I apply len to both sides. And I use properties of len to bring x outside. And now I find the limit of L and y when x approaches infinity. It would be the limit of x times len 1 plus 1 over x. Now if I replace x by infinity, I'll get 1 plus 0. Len 1 is 0, so infinity times 0. And infinity times 0, L'Hopital's rule. You can find in the playlist of Calculus 1 the indeterminate form infinity times 0, you have to bring one of the functions down. So if we take x below and write it 1 over x here, now I'll have, if I replace x by infinity, 0 over 0. And once I have 0 over 0, I can use L'Hopital's formula. And L'Hopital says take the derivative of the denominator and the derivative of the numerator. Derivative of ln is 1 over 1 plus 1 over x times the derivative of 1 over x, which is negative 1 over x squared. Well, actually, I can cancel negative 1 over x squared with negative 1 over x squared, and I can have just 1 over 1 plus 1 over x. And when I replace x by infinity, I'll get 1 over 1 plus 0, which is 1. So ln y goes to 1 when n approaches infinity. This means that y goes to e to the power 1, which is e, if I raise both sides to the base e. And this means that the limit of y, which is this one, is equal to e. Okay, so that's a formula. You can use it always. Limit 1 plus 1 over n to the power n when n approaches infinity is just e. So we have now the ratio test, and we have seen that the limit is e, the limit of a, absolute value of n plus 1 over an, but e is a number greater than 1. So by ratio test, this series is divergent. So we have two examples. We had two examples. This one, the limit was 1 over 3, so the series is absolutely convergent. And here, the limit was e, so the series greater than 1, so the series is divergent. Now, what about the case when the limit is 1? Well, you will see that the limit is 1 whenever you apply the ratio test to P series. Okay, so this is the harmonic series. This is the P series. If you for example uh, apply ratio test here, so an plus 1 over an is 1 over n plus 1 divided by 1 over n, or multiplied by n. Inside the absolute value, there is no need because n starts from 1. And then if you find the limit of n over n plus 1 when n approaches infinity, taking the highest power, the limit is 1. And when the limit is 1, the test fails. Also, you can try with 1 over n square. You will have n plus 1 square, and over you have n square, and the limit will be also 1. So the test fails, the ratio test fails when we use it with the P series. So do not use it with the P series. Use it when we have exponential or factorial. Okay, you use the ratio test. It's very nice there to use it. Very helpful. Use the ratio test to determine whether the series is convergent or divergent. So let us find absolute value of an plus 1 over an. It is n plus 1 over 5 to the power n plus 1 multiplied by 5 to the power n over n. There is no need of the absolute value. I can cancel uh, this one with this one, and I'll have 5 remaining here. So now I can see that the limit of absolute value of n plus 1 over an when n goes to infinity is 1 over 5. I can take 1 over 5 out because it's just a constant, and the limit of n plus 1 over n is just 1. So the limit is 1 over 5, and this is less than 1. So by ratio test, summation an is convergent. Uh, Convergent or even absolutely convergent. Okay, of course it's convergent, but absolutely convergent is stronger. So here we have -1, but when I take absolute value of an plus 1 over an, the absolute value will get rid of the -1. So there is no need to write it. I'll just write 3 to the power n plus 1 over 2 to the power n plus 1 times n plus 1 to the power 3, multiplied by the reciprocal of an, which is 2 to the power n times n to the power 3 over 3 to the power n. And now cancellation. This cancels with this, and I'll have 3 here. This cancels with this, I'll have 2 here. And now the limit of n cube over n plus 1 cube would be 1. So in fact, this, let me write the limit when n approaches infinity of 3 over 2 times n cube over n plus 1 cube would be 3 over 2, and that's greater than 1. So by ratio test, summation an is divergent. Similarly, absolute value of an plus 1 over an would be absolute value of, I have -3 to the power n plus 1 over, I replace n by n plus 1, so I write it 2 times n plus 1 plus 1 factorial multiplied by 2n plus 1 factorial over -3 to the power n. Well, the absolute value will get rid of the minus, and also this cancels with this, and I'll have -3, but the absolute value will get rid of the minus. And here I have 2n plus 2 plus 1 plus 3 factorial. So I can write it 2n plus 3 times 2n plus 2 times 2n plus 1 factorial, and this cancels with this. So actually I can talk about now limit when n goes to infinity of absolute value of negative would be positive. So I'll have 3 in the numerator, and in the denominator I have 2n plus 3 times 2n plus 2. And we take the highest power when the limit, when n goes to infinity. So the highest power below the term with the highest power would be 4n square. And if I replace n by infinity, infinity square is infinity, 4 times infinity, infinity, 3 over infinity is 0, and 0 is less than 1. So summation an is absolutely convergent. This is question 6. If you remember, we solved this series in the integral using integral test, but now we can also solve it using uh, ratio test. So let me find k, uh, ak plus 1. Everything is in terms of k here. So here I have ak plus 1 over ak. Okay. So ak plus 1 would be, let me write this, let me write ak as k over e to the power k. Okay, bring e to the power negative k below. So a to ak plus 1 would be k plus 1 over e to the power k plus 1 multiplied by ak, which is e to the power k over k. And now I can cancel this with this, and I'll have e to the power 1. So now I find the limits. The limit when k goes to infinity of k plus 1 over k times 1 over e. 1 over e is a constant, it will go out. And the limit of k plus 1 over k when k approaches infinity is 1. So the limit is 1 over e, which is less than 1. So by ratio test, summation a k is absolutely convergent, is absolutely convergent. You notice when do we use the ratio test? We always have powers, okay, factorials, okay, like this. So let me find absolute value of an plus 1 over an. You need to practice many exercises and until you understand the method. If I replace n by n plus 1, I'll have n plus 2 here, and this is multiplied by 4 to the power. Well, this is 2 times n plus 1 plus 1, okay? Multiplied by n plus 1 times 4 to the power 2n plus 1 over 10 to the power n. Well, this cancels with this, and I'll have 10 here. And I'd like to understand what is this now. This is 2n plus 2 plus 1. So in fact, this is 4 to the power 2n plus 3. And I can write it 4 to the power 2n plus 1 times 4 square. Okay, so I can cancel this with this, and I'll have 4 square below. And now I can find the limit when n goes to infinity of I have 10 and I have 4 square, which is 16, and I also have n plus 1 over n plus 2. Well, the limit of n plus 1 over n plus 2 is 1 when n goes to infinity, so the answer is 10 over 16 or 5 over 8, and that's less than 1. So summation an is absolutely convergent by ratio test. Now, this is question 11. Let us find an plus 1 over an. I have n plus 1 times pi to the power n plus 1 over negative 3. When I put n plus 1 minus 1, I'll get n at the end. Okay, multiplied by negative 3 to the power n minus 1, and here n times pi to the power n. Well, I have here negative 3 to the power n, and I have here negative 3 to the power n minus 1. So you can write this if you like, negative 3 to the power n minus 1 times negative 3 to the power 1. When you add, uh, you get n minus 1 plus 1, you get n, which is here. And now you can cancel this with this. And pi with pi, and you have pi remaining, 1 pi remaining. So now I can find the limit when n goes to infinity of I have pi, and absolute value of negative 3 is 3. And I still have also n plus 1 over n. Well, n plus 1 over n, the limit is 1. So the answer is pi over 3, and pi is 3.14. So this is greater than 1. And hence, by the ratio test, summation an is divergent. Let us find absolute value of an plus 1 over an. N plus 1 factorial over n plus 1 to the power n plus 1. We just have seen this question, few examples above, but I think it was n to the power n over n factorial. Well, I will have n plus 1 factorial over n factorial. These two can be cancelled because here I have n plus 1 times n factorial. And now I can write it as I have n plus 1 to the power 1, n plus 1 to the power n plus 1. So I have n to the power n over n plus 1 to the power n. And now to find the limit when n goes to infinity of n over n plus 1 to the power n, if I divide by n the numerator and the denominator by n, I will have 1 over 1 plus 1 over n to the power n. And this is in fact 1 to the power n is 1, okay? And the limit of 1 is 1 over limit when n goes to infinity of 1 plus 1 over n to the power n. And I have just told you that this limit is e. We evaluated this limit and the limit was e. So the answer is 1 over e, and this is less than 1. So by the ratio test, summation an is absolutely convergent. Another example, let us find an plus 1 over an. N plus 1 to the power 100, 100 to the power n plus 1, n plus 1 factorial. Actually, there is no need of the absolute value because everything is positive multiplied by n factorial over n to the power 100 times 100 to the power n. Let us see how can we cancel. N to the power 100, n plus 1 to the power 100, okay. This one with this, and I have n plus 1. 100 will remain here. So now I have limit when n goes to infinity of, I have 100 over, let me say over n plus 1 times n plus 1 over n to the power 100. Let me write it like this. Now this would be equal to limit of this times limit of this. Limit of this one, 100 over infinity, that's 0. Limit of this one is 1. Limit of n plus 1 over n is 1. 1 to the power 100 is 1. So the limit is in fact is 0, and 0 is less than 1. And by the ratio test, summation an is absolutely convergent. One last question about the ratio test. Let us find an plus 1 over an, the absolute value, everything is positive here. Okay, so I have 2n plus 1 factorial over n plus 1 factorial. Uh, Whenever you have factorial, you immediately use the ratio test. Times n factorial square, okay, over 2n factorial. Well, here I have 2n plus 2. So it's 2n plus 2 times 2n plus 1 times 2n factorial. And here I have n plus 1 times n factorial. So in fact, I will have 2n plus 2n factorial will be cancelled with 2n factorial. So I have 2n plus 2 times 2n plus 1 times n factorial square. And I have below n plus 1 square times n factorial square when I distribute uh, degree 2. Okay, so these two cancels. And now I can find the limits when n goes to infinity of 2n plus 2 times 2n plus 1 over n plus 1 factorial. And how do we usually find this limit? We take the term with the highest power. The term with the highest power in the numerator is 4n square and here n square. N square cancels with n square, and the limit is 4, but 4 is greater than 1. So by the ratio test, summation an is divergent. I hope you had enough examples about the ratio test in this video.